So as you see here, the title is actually very generic. I don't have any specific title. So the reason being that I just wanted to go through the work, what we have done in the last 5-6 years, and then how much we have contributed to this particular title. So that's the reason why I kept this title is very generic. So as you see here, we're more working on this supramolecular gels. So before we go into that, what are the other areas we are more focusing on this? So these collagen mimicking peptides, we try to mimic the collagen with the smaller peptides. As you know that collagen is a biomolecular system. And also we're working on this peptide-based surfactants. Recently we have some attractive, interesting data on that. And also we work on this amyloid fibrils and this inhibitions. So all of them actually centered around this molecular self-assembly process. So that's where actually we are more focusing on that. So let's get into the topic. So I think maybe some of them covered this particular the polymerization. So we all know that the polymer is a high molecular weight compounds which comes from the monomers, where they are actually the monomers are linked through the covalent bond, right? So if you look at that, if somebody thinks about that, I want to mimic this polymer, but without having this covalent bond. So earlier, actually, maybe a couple of decades back, people were wondering that how it is possible. But nature actually inspires us that, there is a possibility for making such a kind of a polymers without having the covalent bond. If you look at the cell membrane, so this is actually made up of the small lipid molecules. The lipid molecules is very low molecular weight, right? But it makes that such a big actually structures. If you carefully look at it, there is no covalent bond between this. So how this nature makes this particular lipid molecules assemble into the bilayer is actually telling us that there is a possibility you can still make a bigger molecules or supramolecular system using a small molecules. Not only that, even we know that the DNA is a double helix. If you see that there is an interaction between this single strand, between the single strands or actually the hydrogen bonding, right? So actually this also actually tells us that by using this molecular self-assembly process, you can build this molecule. Not only that, there are proteins which are actually functional only if there is a dimer or trimer or tetramer. I think, the last talk was actually talking about this dimer, tetramer, etc., right? So basically what nature tells us that, if you have a single molecule, which is not a functional one, but when it is assembled here, it can convert that from the functional, non-functional to the functional one, right? So keeping this in mind, so when the molecules, the small molecules get assembled, right? So it can form like a polymer-like chain. Right? So when it is in the aqueous solution or any organic solvents or something, so because of this assembly, the whole hydrophobicity of the molecules is getting increased. As a result, this will get into the solution, get into the phase separation. As a result, it will come out from the solution. So in some cases, what happens, these supramolecular systems actually forms a polymer-like system, and then it entrap the, immobilize the water molecules. So that is actually ended up with the gel. So gel is nothing but the three-dimensional structure, three-dimensional molecules, which has a viscoelastic nature. So generally the gels actually, if you look at this, many of the people know that, it comes from the polymer, which are actually covalently linked. But there are other categories where the physical castings, what I'm talking about here is, it can be classified into three categories. When it is immobilize the water molecules, we call it as a hydrogel. When it mobilizes the organic solvents, we call it as a organogel. But there is an intermediate class where we call it as the ambidextrous gelator. That means it's a single gelator which can gelate water molecules as well as the organic solvents. There is n number of gelators were there for hydrogel. There is n number of gelators for the organogels, whereas very, very, very few numbers are available for the ambidextrous gelators. The reason is there is no kind of a molecular structure and the gelation correlation. It is very difficult to predict a molecule whether it forms a gel or not. So that's actually the basic understanding is actually missing now. So why we should worry about this supramolecular? Why we are interested about this supramolecular system? If you look at that, there are actually several fields actually now these supramolecular gel systems are actually used. You can see that the tissue engineering is one of the prime, the area where this gel system is actually, because it is extracellular matrix is actually mimicked with this three-dimensional gel systems. So not only that, even for the drug delivery, it is actually now people are considering that. And then also there are several other, the areas where the supramolecular gel systems are actually used. Particularly when you look at these hydrogels, these are actually, you can find that, all these areas are actually, very important, and then very, very, productive way, you can get these things. So similarly, this organogel is also having this lot of, other applications, right? So what is other actually, when you look at this, the academic industry, so right? So the academy has a different kind of a view on the supramolecular gel systems, whereas the industry is also interested, but they have a different kind of systems. But why industry is now looking at this supramolecular gel systems? Because this, as I said in the previous slide, this supramolecular gel system having wide applications, still the area is getting increased. Wherever possible, these gel systems are actually, even the solar cell also, they are trying to implement this kind of hydrogel systems. So, and it's also cost effective, and then also it's biocompatible, because if you, depending on the molecular system which you are choosing, this will be compatible and then non-toxic, eco-friendly, easy synthesis, and then wide applications. So if you look at the academic perspective, what we look at here is a fundamental understanding. How these small molecules form the gel. So how these polymers are built. What are the forces actually is driving that? So why certain molecules only forms the gel, not all the molecules? So then also we are interested to create a novel gelators depending on the requirement or maybe any target applications. So one of the important actually the advantage of the supramolecular gels, I will be talking about the next slide, is the stimuli responsive. So if you have any kind of a stimuli like the pH or the temperature or the salt or any metal, that will be very sensitive. So using that stimuli responsive nature, this supramolecular gel systems actually very useful. So and then there are a lot of extending applications. If you look at this, the US, you see that it's not like a very drastic change in this supramolecular systems area, right? So why supramolecules? We all have these polymer systems, but there are several advantages when you think about the supramolecular gels. So the first one is the chemical modification, because it requires very small molecules. You're not going to spend a lot of time for the synthesis and then making this. So the second one is the critical gelation concentrations. Generally, you need a lot of samples for these polymer-based gel systems. Whereas here, you can have a very, very low concentration sample, which can immobilize large number of water molecules or maybe any kind of organic solvent, something. Then the very interesting thing, what I told you in the last slide, is a stimuli responsive. Stimuli responsive, as I said that, the pH, temperature, metal, anything you can do it. Depending on your requirement, you can tune this. Then the gelation kinetics. So convenient for the tuning. One of the important, properties of this supramolecular gel is depending on your requirement. Let's say like I need very high stiffness gel. I don't need high stiffness. I need only very weak gel. So all these can be tuned by just tuning these kinetics. Then similarly for this chemical crosslinks, there is no chemical crosslink is required here. So if you look at any polymer system where they use any bifunctional molecules or something to increase the polymeric length, so that can immobilize the solvents. But here there is no chemical crosslinks is required, because whatever the molecule you are choosing, that is more than sufficient for making the polymer-like structures. And then it's very dynamic. If you look at that, once you break the gel, most of the gels comes back. So that's a self-healing kind of a things. That is actually the advantage for this. So there are so many advantages with this supramolecular gels, right? So we are interested in this supramolecular gel systems. When we look at the literature, there are several small molecules have been already proposed, right? So in this, actually, we are interested in amino acids and then peptide-based systems. Peptide means actually very short peptide-based systems. So the reason being that, so as we all know that amino acids are actually the building blocks of the protein. So there will not be any toxic problem. And then it's also ion biocompatible and also easy to functionalize, because it has two functional groups. One is carboxylic acid, the other one is amine group. So you can easily functionalize this amino acid. Similarly, the peptides, you can see, these are biocompatible, and there is a low immunogenicity, and then high target specificity and selectivity. That means the peptide sequence, what you are choosing, if it wanted to target some places, you can tune the sequence, specifically. Then it is a low accumulation in tissues, because it is undergoes the proteolytic cleavage. It will not stay for a long time, and also easy to functionalize, similar to the amino acids, right? So now, what is the question we are going to address? So what we are going to address? So what is the question we are going to address? So there are several actually amino acid based systems are available. If you look at this slide, there are almost 22 amino acids are there, but the amino acids which forms the gel is containing only, is having only 6 amino acids, right? So all of them is actually functionate with the fluoronyl methoxycarbonyl. So this aromatic system is facilitating the pi-pi stacking interactions. But despite that, despite 22 amino acids, only few of them is actually showing the gelation properties. So the remaining then are not showing the gelation properties. Why? So what could be the reason? Right? So that's what we are going to address. As you know that this is a self-assembly system, which is actually mainly driving the force with the hydrogen bonding, aromatic and other things. So first what we wanted to focus here is to look at the hydrophobicity. So the aromatic, the amino acid side chain you see, polar, non-polar, ionic, all these actually the variety of amino acids are there. So what we started to look at it, how this hydrophobicity of the side chain is actually influencing the self-assembly property and thereby the gelation. So the first one is what we're looking at as the methionine amino acid, which is functionalized with the F mark, where actually we slightly change the sulfur to CH2. So this is the F mark non-leucine, right? So and then we oxidize this sulfur to the sulfur dioxide. The reason is this is actually electronegative atom. This is more actually non-pair nature than this one. When we oxidize the sulfur dioxide, this is actually more hydrophilic than this one. So we have two systems. One is more hydrophobic, and then the mid one, and then the more hydrophilic. Then this one system is actually we have chosen in order to look at that whether this fluoronyl group is required for the self-assembly formation. And then when you look at this, both of them are aromatic. So in case if this forms the gel, then we need to look at whether the aromatic system is required. So for that we have chosen the tertiary butyl group, right? So the results are very interesting. So this F-NOC methionine has actually formed the gel. So this is basically the vial inversion test. So visually you can check whether the solution forms the gel or not, right? So when you invert the vial, so the gel will stay on the top of this one, right? So if you just change this small electronegative atom to the hydrophobic system, you see that there is no gelation, right? So when you oxidize this, it still forms the gel, right? So whereas if you replace this fluoronyl group to the benzene, so it is not forming the gel, so it's a liquid. So similarly for the tertiary. So what this tells us here is, if you change a slight change in the hydrophobicity of the side chain, you can convert the gelator to a non-gelator. So now, whatever the concentration you are looking at here is the minimum gelation concentration. So that is the minimum gelation concentration is required for the formation of the gel. If you look at this, it's only 0.8 millimole. If you look at this, it's 8 millimole. So what happens here basically, we are altering the balance between this aromatic system with the hydrophobic system. So the balance here is different, right? So that indicates that you need a more concentration to make the gel. So by looking at this, we understand that any change or even a minor change in the hydrophobic system, in the side chain, will lead to different kind of a response. So that is actually the pictorial representation, but experimentally we need to confirm that whether this has a viscoelastic nature. So we did this, rheological studies. As you see here, this is the amplitude. We typically use this as a starting measurement. So where the G prime, which is actually the storage modulus, the G double prime is the loss modulus. So for a gel system, G prime is actually always greater than the G double prime. So that's what we see here, this amplitude sweep. And then we also check the time sweep. So how long it takes to form the gel. So when you look at here, this takes like almost 30 minutes for this system to form the gel, right? And also we looked at this frequency sweep, which is actually another parameters to look at is there any dependency in the frequency for the gel to display. If you look at this this graph is actually the step stain sweep. This is basically for the thixotropic nature, right? So once you break the gel, whether it comes back or it's a self-healing property. So this is the experiment we do. So basically you apply a very small amount of the stress in the beginning. So where G prime is greater than the G double prime. So when you increase the stress to 100%, so you can see the reverse in the G prime and the G double prime. So when you release the strain, it comes back to the. So the time that we give here is 2 minutes. So you keep this gel under the high stress, you convert it into liquid form. As soon as you release the stress, it comes. So like this, we do like 2 or 3 cycles. We see that whether it comes back this property. So that's how we confirm this regeneration properties. So all we are looking at is actually the molecules, right? But once you put it in the the liquid system, it converts into the gel form. So we confirm that whether the self-assembly is happening in the system. So this is the atomic force microscope. What you are seeing here is actually lentifibrils. It is similar to what we see in the polymers, all right? So this is basically the responsible for immobilization of the solvent molecules because the solvents have the capillary action with these fibers. So that's why thereby the solvents are actually getting immobilized. So we do a lot of characterizations to understand how these molecules are self-assembling into the fibrils. So what you see here in the top is the fluorescence spectroscopy. So there you can see that this 312 is actually corresponding to the particular monomer. Once this self-assembly occurs, then you can see the red shift that indicates that there is a FMOC group which is actually getting pi-pi stacking. So similarly, we do this circular dichroism, which basically is an induced circular dichroism. If you have a single monomer, you don't see anything, any response, because the pi system is getting assembled. So you get the induced circular dichroism. This is a peak which is corresponding to this particular fluorinary group. And also we check, is there any hydrogen bonding? Because in the system you see that there's a amide group here, and then also the COOH group here. So is there any driving force from this hydrogen bonding? So that's information you get from the FTIR. You can see here this is 1716, which is corresponding to this particular carbonyl group. Once you have this gel, you can see it is shifting to 1618 and 9 centimeters inverse, which is telling us that there is hydrogen bonding between this. So based on this experimental, and also we do this power XRD, which confirms that this pi-pi stacking is there. So we're looking at this 0.33 nanometers for the aromatic stacking. So we believe that, based on this experimental data, this could be the, arrangements of these molecules, which leads to the entanglement of the fibers. Right. So the next is actually what we wanted to focus is, we have focused the hydrophobicity. Yes, it is a very important for this self-assembling system. So next we wanted to focus how this aromaticity is very important. So for any protein, if they wanted to understand, so they will focus on, depending on the function or something like a phenyl groups or maybe aromatic amino acids, by replacing it with the aliphatic amino acids to understand how this particular amino acid is responsible for that. But what we want to do here, we don't want to change this system completely to understand the aromatic system, because when you change this, then totally you are changing the amino acids, right? So you can't get really the effect of the aromatic aromaticity for the gelation process. So what we did is we simply removed this aromaticity from this. So we have the cyclohexyl ring here, right? So let's see then what's the effect. So what you see here is actually the FMOC phenylalanine, which is actually well-known gelator, which forms. So when you replace this particular benzene with the cyclohexyl ring, so you see that, it forms the gel. But the interesting observation here is within 20 minutes, it actually converted into the liquid form. So accidentally, the students actually heated this one, because she was worried that, she was not able to get the gel. So she heated this one, and then again she got the gel. But what happened, overnight, it again turns to the gel solution. So again she did that, okay, we'll just heat it one more time, and then you see that over the 2 months this becomes stable. So what could be this, what is making this is a big difference when you are just shifting, one cycle to the other cycle to the other cycle, right? So what we did is actually we looked at these electron microscopic images for the corresponding solutions here. You see here, the first time when you are making this, it's not forming a very entangled fibers, which is required for the immobilization of the solvent molecules. But whereas when you are heating the second time, right, there is some kind of a fibers is started forming. But whereas in the third time, you can see the highly entangled fibers. That's why this gel is actually more stable, right? So the heating actually is very important. And then which also, corroborated with our AFM microscopic images. So what is the effect we are getting by changing this aromaticity, right? So FMOC also forms the gel, but after 2-3 cycles, this also forms the gel. So that means aromaticity is not required, right? So that's the question we asked. Then we looked at this thermal stability. So this is actually again the vial inversion. Sorry, the image is not very clear here. This is the vial inversion test. You increase the temperature, right? And then you can see that at 65 degrees, this FMOC phenylalanine which melts to the liquid. Whereas when you look at this FMOC char, which melts at 50 degrees. So there is a 15 degrees difference between this aromatic characters when you have the difference, right? So that indicates that people, when you are looking at this aromatic benzene ring, aromatic system, so that basically helps to increase the stability of the system, rather than it is not, giving much importance for the formation of the gel, right? That's what actually the information we get. So the aromatics have the phenyl to increase the thermal stability of the supramolecular gel systems, right? So we looked at the hydrophobicity. Very small change in the hydrophobicity will influence this hydrogel system. And also we looked at the importance of the aromaticity. Then now we wanted to look at the significance of the FMOC group. Right. So there are so many systems which has been reported with these FMOC groups. they have said that is one of the highly promoting system. If you, in case if you are looking for any hydrogel small molecules to convert into the gelator, you can use this. But we learned from the previous, the first slide of this working thing. Even though the FMO group is protected with all the amino acids, only few amino acids are forming the gel. So that means it is extending. It is supporting for some time. To some extent, but not for all the time. So what we did was, we actually thought of that, why can't we have one more FMO group in the system, right? So for that, we have chosen this lysine because it has the two functional groups, two amino groups, which is easy to functionalize. So you can date this amino structures like one FMO group in this amino terminal, the other one is the side chain. So by incorporating this, actually the fluorenyl group, we are also introducing the additional hydrogen bonding, right? So what we get from this? So we are introducing the additional pi system, also introducing this additional hydrogen bonding. So the expectation is like this. So since we have a large number of aromatic system now, and also the hydrogen bonding systems, we expect that this particular gelator may gelate both water molecules as well as the organic solvents, right? So, and also we know that, as I mentioned before, these FMO amino acids are all actually showing only the hydrogels. There is no organogels for that. So, and also the ambidextrous gels are very, very rare. So the idea of, putting this is actually increasing this pi systems as well as the hydrogen bonding, which may help us to discover or maybe find a new ambidextrous gelators, from the amino acids, right? So, but just having this may not help us that whether this actually playing an important role for in case it turns out to be ambidextrous gelator. So for that, we built another 3 molecules. So just we replace this FMOC with this phenyl ring, and then there's a tertiary butyl, and then without this. This is the FMOC lysine, right? So when you look at the response for this particular modified system, you see that very interestingly, as we expected, that this forms a wide, hydrogel in a wide range of a pH. Not only that, you can see that some of the organogels is also, organogels formed from some of the selected organic solvents, right? So that means by introducing this kind of additional pi system in a gelator, you can basically convert them from a normal gelator to a ambidextrous gelators. So if you look at this and this and this, you can see that the FMOC, the block, actually this is a 1, which doesn't have any kind of, this is a liquid which is actually in the bottom of this. There is no gelation for this. So that indicates that this is very, very important for that particular ambidextrous gelator, right? So when you look at this one, so this forms the gel at pH 6, whereas pH 7.4 it's not formed. So and also this is a very weak gel, based on the rheologist data. So this helps to some extent, but it is not, very good in all the pH range. When you look at this FMOC lysine alone, it doesn't have any, right? So by substituting the FMOC group in a system where you have other FMOC group, which basically converts that into ambidextrous gelators. Right? We confirmed that with the rheology data. What you see here is the angular frequency sweep. So you can see that it's a pH dependent. So the pH 6 has the more viscoelastic nature because the G prime value is very higher than the 7.4 and then this 8.8. Interestingly, I think this pH 6 is showed as a complete, almost 95% of the recovery of the gel, whereas the other 2 pHs is not as good as the pH 6.1. So that indicates that this thixotherapy is actually the pH dependent for this system, right? These are the microscopic images. You can see the fibrous nature for all the pHs what we have got the gel, right? So, but each of them has kind of different kind of morphologies. One of them is skin-like a morphology here, and then this is actually fibrous-like, scaffold-like morphology here. So here is a non-porous, and then some crystalline natures is also, observed in this case. So the another important property when we go for the supramolecular gel system is to look at the temperature, right? So you imagine that, we are using these water molecules for immobilizing this. And then if you take any polymer system, you can heat up to 100 degrees or 150 degrees or 200 degrees something. But you look at this, at pH 6, even at 100 degrees, 90 degrees or something, 95 degrees, 100 degrees, this gel is actually, still stable. So that means the interaction between these water molecules and this gelator is very strong. So which holds this at pH 6 is nearly high temperature. But again, this the temperature, the T gel is actually depends on the pH. It decreases with increasing the pH. Okay, so the reason is at higher pH, this particular molecule actually there is a COH group here. So this at high pH, this will be a COO minus. So which will be actually a repelling nature. Whereas when you decrease the pH, this negative charge is getting converted into the neutral. There's a COOH form. So that's why this pH dependent effect we observe for that, right? So I'm not going into this characterization as I discussed this before. So going back, going to the possibility of the molecular arrangement, right? So there are two possibilities. One is the parallel arrangement. The other one is the anti-parallel arrangement. So because this is not the symmetric molecule, because the COH is somewhere here on the left side. So what we proposed was either this A, the fluorine moiety has been stacking with this B and B, and then A and then B, and the head to head or head to tail. So this can be in a parallel orientation or this can be in anti-parallel orientation. But unfortunately, it's very difficult to just find out what kind of a structure is actually present in the system. Right, this is actually the electron microscopic image for the organogel. Actually, similar to the hydrogel, this also forms these fibrous kind of natures. Right. So now coming to the other the topic, we know that this addition of this FMOC group is converted that small the gelator from the hydrogelator to the ambidextrous gelator. Now we thought that okay, we can just instead of just doing some replacement, why can't we go with some functional moiety, right? So which can be used for some specific applications. So now we replaced this particular system with the pyrene. So this pyrene is very well known dye and has been used for many applications. And then this is a biotin, which is biologically is very important molecules. And then this biotin is bioavailability is very less because it's a poorly soluble in water system. So if anybody gets this, a biotin in a gel form, that will be more applications that can be fine. So here is actually the importance of the pyrene and this biotin. So as I said, this is a precursor for many of the dyes. And also these fluorescent spectroscopy. This can be used as a staining agent, and also this can be used for the charge transfer because it's an electron-rich system. For any charge system, you can use it. Similarly, for this biotin, is actually necessary for the cell growth, and then also it assists the various metabolic reactions, and particularly this acting as a receptor ligand interactions with the avidity and the cyclodextrin and other things. So based on the previous experience, if we get some kind of a gelation from these molecules, that will be more interesting to for several applications. So as you see here, this is a similar system as what the FMOC di-FMOC system what I showed you. So the results, we use this TNF, trinitrophenylene. Actually, this is a electron deficient molecule. So what the idea here is, this is the electron rich center we have. So once we have this electron deficient center in the system, so whether this can convert, transfer the charge from this to this, right? So what you see here is the hydrogel, right? And then it also forms the organogel, right? So now if you add this acceptor here, so this turns into the brown. That is an indication for this charge transfer from this pyrene to this. Not only that, we also subjected that into the UV radiation. So you can see here, without this TNF, this shows the fluorescence, whereas when you add this actually the fluorescence is quenched, right? So that happens for this organogel system also. So the model what we propose here is, so basically if you don't have this TNF, this is a system, this arrangement, and then when you have this TNF here, so that's intercalating between this two pyrene system, therefore the charge is actually transferred from this pyrene to this TNF, right? Then the biotin part, actually we are lucky that we got the hydrogel here. So in the literature, very difficult to get. You can find this biotin based hydrogel systems. So very importantly, at the physiological pH, we got this the gel, and then this is look at this electron microscope image, which shows a nice fibrous structures, and then this viscoelasticity of this hydrogel was confirmed with this rheology experiments. And this is actually the model is proposed as similar to what we have done, what we proposed in the last slide. So now we have done 3-4 systems, right? Similar systems. Now what we wanted to look at here is attempt to develop a correlation between the molecular structure gelator and the ambidextrous gelation. So far, it is very difficult. If somebody gives you a molecule that if they ask you that, I mean, whether this molecule forms the gel or not, it's very difficult to predict. To some extent, you can say, but most of the time it is very difficult to say. We can say that the molecules can self-assemble, but whether it immobilizes the solvents to convert that into the gel, that is a question mark. We cannot predict. So, but here what we try to do here is whether we can get some correlation, structural correlation with the gelation system. So for that we kept the same the di-up walk, but we replaced that lysine with the diaminopropionic acid. So the difference between the lysine and the diaminopropionic acid is here is only one CH2, there is a 3 CH2 in the lysine case. So basically to change this system, maintain this. So interestingly, I think this also forms this ambidextrous gels. You can see that from 4.9 to 9.1, it very nice gels actually forms, right? So also this forms the organic gels, right? So once, after getting these results, we went back to the literature and then we pulled out, what are the ambidextrous gelators are, reported, right? And then just see that, is there any correlation between these gelator systems? So when you look at this, all these systems where you see this color, right? These are all aromatic systems. And then these are actually the hydrophobic system, but it is actually, the alkyl chains are there. So now if you look at this, looks like this is something like a dumbbell system. Right? So if you look at this, all these molecules, it can be aromatic or hydrophobic, except this system, you can find that this shows this dumbbell system. So what we propose here is, if you design a molecule with this pipe, this kind of dumbbell shape, and then with either both the side aromatic, or one side is aromatic or the other side is aliphatic, or the vice versa, with this some hydrogen bonding capacity in between this, and then one polar, right? So that actually you can expect that it can act as an ambidextrous gelator. So this actually work was published in the on the cover page of this journal. Right. So we quickly I'll just move to maybe I have another 5 minutes. 5 minutes. Yeah. So I think most of you know that this amyloid system, which is actually basically comes from the protein, which is actually getting unfolded. This unfolded actually proteins is unstable and then becomes a beta sheet. The oligomers, which actually converted into the fibrils. Right. So these amyloid fibrils are responsible for many diseases. Right. So what happens basically, once this fibril forms, this will get phase separation out in the solution. You get the precipitate kind of things, right? But what we wanted to here is, we want to convert this amyloid fibrils into the hydrogelator. Right. Why? Because this particular amyloid-based peptides are having an inherent property of this self-assembling into the beta sheet structure. So using that, actually, whether we can convert them into the for the 3D hydrogels. So what we did was actually we have selected this NFGAL. This is coming from this highlight amyloid peptide fragment, right? So we did actually the gelation test for this after adding this, conjugating with this F molecule. Right. So the interesting thing here is this minimum gelation concentration. So any applications for the biological applications, we have to look at the concentration, because the gel, if you have very high concentration, that itself will be a toxic. So if any of the applications, we always look at this minimum gelation. So any gelation which is less than 1.1% in this supramolecular gel field, we call it as a super gelator, because very difficult to get minimum gelation concentration less than 0.1. Right. So interestingly, after conjugating this, actually this, to this peptide, it is actually forming the, minimum gelation concentration, which is less than 0.1. So here in this case is a 0.08. Also, it showed the pH dependency. So anything is actually above 6.5, it forms a nice jelly. So we confirmed this with the rheology, right? So the important thing, what I wanted to point it out here is, generally the solution will convert to the gel. Here as also it happens, but as soon as you add the solvent to the system, but it immediately it shows the difference between the G prime and G double prime. So that indicates that addition of this particular peptide is having a faster, kinetics for the self-assembly that leads to the hydrogelation. So the fibrillus is confirmed with the electron microscope, and then we propose this actually the structure based on the biophysical characterizations. Right. So now we move to the other peptide. Right. So this is actually alpha-synuclein fragment. So this is actually one of my PhD student. We're sitting here. For her PhD work, she started working on this system, right? So this is a system entirely different sequence, but after conjugating this to this sequence, you see that this is 0.03. That's a 0.3 milligrams per ml. Actually, that's very interesting that, to see that what you have conjugated only one FMO group, that's aromatic system, which actually not only converting that into the hydrogel, also it shows this minimum gelation is only 0.0, right? So this actually, made us to think, go back and then look at this sequence. That is there any, because this is also a supergelator, which is actually showing low minimum gelation concentration. This also does the same thing. Is there any commonality between these two sequences? Right? Although these amino acids are different, there's one amino acid which is similar here, which is actually next to the FMO. So that is asparagine. So you all know that, now the supramolecular self-assembly is facilitated by various intermolecular forces. One of them is hydrogen bonding, right? So in this sequence, the common is asparagine, right? So we thought that, okay, there is maybe a triggering factor from this site in CONH2, which is influencing this actually the gelation system. So what we did was we replaced this particular asparagine residues with the different amino acids, right? Keeping in mind that phenylalanine is facilitating and also completely removing the aromaticity. And then this is a glutamine, which is actually one CH2 is actually more than this asparagine, right? When you look at the results, it's tabulated here, sorry, it's very small. Except this asparagine, the remaining are all actually 0.1, 0.2 and then 0.6. Right? So if you just change this particular amino acids, which is drastically changing the minimum gelation. So that indicates that this is actually the asparagine is playing an important role for this one. Right? And then we went back to this old sequence that the NFJL. There also we did this similar kind of experiment, and then you see that the remaining all of them is showing very high minimum. So that indicates that the asparagine is actually a very, very important role in reducing this minimum gelation concentration. So now I just finished this with the questions to address with this particular part. So now knowing that, okay, this asparagine is playing an important role, is there any direct intermolecular hydrogen bonding between asparagine side chain, which is actually facilitating this gelator into a supergelator? Or if not, is there any hydrogen bonding between asparagine side chain and the water molecules? And then, is there any water-mediated hydrogen bonding between asparagine side chain? So, if not direct contact, is there any water-mediated hydrogen bonding between which facilitate the self-assembly process? Is there any hydrogen bonding network between the difference between the asparagine and glutamine? Because both of them is having the same CONH2, but asparagine is actually the supergelator, but not the glutamine. So with this, questions, we went for this molecular dynamics, which is under the process. So with this, I stop here and then thank you for your attention. If you have any question. Okay, so before that, I just wanted to thank the people. So we thank the CSLRA for allowing us to do this work. And then the first part of this amino acid work is actually carried out by my PhD student, Murli Mohan Reddy. And then the second part is actually the Jaini flora. And then the last peptide part is actually Anaga. And then we thank Abhijit for extensive help in characterizing these hydrogels for the rheology experiments. And they are all actually the student of Abhijit. Thank you all.